Hello to everybody. Welcome to today's program, Can Science Save the Planet? A Technion Earth Day webinar. My name is Professor Noam Adir, and I'm the Executive Vice President for Research at the Technion. We're coming to you today from the Haifa campus of the Technion in Israel. As I'm sure that all of our audience is aware, Israel has been at war for the last half year and leading up to the latest failed attack from Iran. The October 7th attack and all those killed, injured, displaced, and taken hostage are constantly in our thoughts. Thousands of Technion students, researchers, staff, and faculty have served and continue to serve in our reserves, many of them for many months. We wish to thank all those that have enabled the Technion to continue its important tasks of teaching and research, and fervently hope for the return of all of the hostages. I've been a member of the Shulach Faculty of Chemistry in the Technion since 1995, where I proudly hold the Bertha Hertz-Axel Chair in Chemistry. And I'm the head of the Macromolecular Research Lab. Before joining the Technion administration in my present role, I had the honor of serving as the Dean of the Faculty of Chemistry for 6 years. One of the great joys of being the Dean is having the opportunity to recruit some of the best and brightest young scientists as new faculty. We will meet 3 great young scientists today, 2 of them from my own faculty of chemistry and 1 from the faculty of civil and environmental engineering. Saving the planet is not just a trendy catchphrase. It is a goal that many of us truly wake up with every morning and go to bed with after a long day in the lab and the classroom. It is a goal we try to impress on our undergraduate and graduate students, and it serves as a focus point for the research we do. As the VP of Research, I have a unique view of all of the research taking place across our campus. And I can safely say that almost all of our researchers keep this one major theme in our mind. How can we improve the quality of human life while actively working towards a cleaner environment? And if I can have the first slide. No? Okay, if I can have. Yes? So I don't think that it's hyperbole to say that we are living in a time of extreme climate change. Every day we see extraordinary news about flooding, fires, pollution, drought. The list goes on. With the health of the planet in jeopardy, the Technion has dozens of researchers working across disciplines to tackle issues affecting all of us on a daily basis. As we approach Earth Day on April 22nd, I am proud to introduce a few of the incredible people at the Technion whose research is having and will have an impact not only in Israel, but worldwide as we work to reverse the current environmental crisis that is affecting us all. Assistant Professor Charlotte Vogt, head of the Vogt Laboratory of Catalysis for Fuels of the Future. Associate Professor Charles Dizendroek, head of the Dizendroek Lab researching polymer mechanochemistry, and Associate Professor Adir Dian, head of the Soil and Environmental Chemistry Lab. I'd like to remind all of our audience coming from all over the world that at the conclusion of the presentation, Mary Ellen Titiani, the ATS VP for Campaign Strategy and Donor Relations, will join us to moderate the questions from you, the viewers. Please use the Q&A function located at the bottom of your screen to submit your questions throughout the webinar, and we will answer as many as we can. And now, on to the webinar. The Technion has dozens of research projects that are relevant for today's subject, but we only have time for 4 of them today. But if you write in your favorite browser, Technion and Sustainability, you will find a website that will lead you to the themes, the research, events, and news in the field. It is a true cornucopia of ideas, discoveries, and inventions of some of the brightest and most imaginative minds you can find anywhere. I've been asked, and it's really my honor, to not only be the moderator today at this point, but also to highlight the research taking place on campus and share a bit of the work done in my own lab. A big part of my research deals with finding a way to create a truly green source of renewable energy. In fact, we call it the greenest energy because it comes directly from photosynthesis, the biological mechanism of turning sunlight into chemical energy. So basically what we're trying to do is to replace many of the solar cells that we see today in many places along the world using photosynthesis. Now, what is photosynthesis? For that, you're going to have to come to the Technion and take one of our courses, because it takes a little while to understand the entire process. But just remember that when you go outside and you see the plants and you see algae in a pond or a seaweed in the sea, you're seeing photosynthesis. You're seeing an organism taking the energy of the sun and turning it into a storable chemical fuel. It might be a sugar, a carbohydrate, and it might be some other type of fuel. What would happen if we could actually use that? So people have been using photosynthesis as their source of energy for thousands of years. You can go back to the days of the caveman that found a way to harvest and use fire. He was burning something that came out of photosynthesis. And then more recently, we discovered how to use, unfortunately, but for the benefit of mankind, coal and gas and oil. And most of that came out of organisms that were either photosynthetic or ate something that was photosynthetic. So it's all basically coming from the sun. And more recently, a lot of people have said, well, let's maybe use something that will be less polluting. We'll actually take some of the carbon dioxide from the atmosphere, we'll grow a plant, and we'll use that to make a biofuel. So we call that carbon, when we give off carbon dioxide, we call it carbon positive. It's giving off carbon dioxide. When it's not giving off carbon dioxide, or we're staying the same amount of carbon dioxide, it's carbon neutral. But what would happen if we could actually absorb carbon dioxide? We could actually make the atmosphere better. So this is our idea. My good friend, and I'm going to show you in a moment, Gadi Schuster and I, about 15 years ago, thought, what would happen if we could actually take the energy directly out of plants without burning anything, no combustion whatsoever? What if you could stick something photosynthetic, something truly natural, into an electrochemical cell and make electricity? And maybe using this electricity, we could also make a fuel, let's say hydrogen. Hydrogen would be a nice fuel to make, because when you burn it, you get water. So that would be great. So what we need is a photosynthetic organism, something, a plant, somehow take the material, somehow get the electrons out, and somehow get fuel. That's a pretty big plan, and it takes a long time to develop such a plan like that, and I won't go into all the details. And of course, it needs great friends, and here we see Gadi, who's from the biology department, and all of the work that we've done has been a joint project with him. So over the last 15 years, we've discovered that we can do this. We can actually take out electrons from a photosynthetic organisms. And what are these organisms? Well, some of them are bacteria that we don't see them, but they're all around. Some of them are green algae. You can see them sometimes as scum in a pond. They're nice and green. We can take them out of algae in the ocean, which we just typically call seaweed. And seaweeds are really fantastic, and I'll say more about that in a moment. And we can even do that from plants. We can even take out electricity from cacti. So there's many, many different ways we can do that. And each type of different plant or organism, we do it slightly differently, but the process is basically the same. We can also use isolated systems, but I won't go into that today. And if somebody's interested, I'd be happy to talk about that. So basically, what you also need, so you need a plant, and you need a few people to have the ideas, and you need some good government institutions to fund us, but you also need students. And here I have a picture of Yaniv Schlossberg, who was a great PhD student who did a lot of the work I'm talking today about, because basically he was the one that said, why don't we use live organisms? And he basically was able to show that we could get electricity from all of these different organisms. And the most important one was seaweeds. Now, seaweeds are great because, first of all, they grow immensely fast. I think that all of you know, when you go to the beach, you see all these seaweeds around. Where did they come from? They grow from CO2 or from carbon dioxide in the atmosphere. They live in salt water, so they don't need fresh water. You don't have to give them any fertilizer. You don't have to give them anything, and they work just great. This is one that's called ulva. It's also called sea lettuce. It's actually quite tasty, and there's a big there's a company that actually grows this and uses this as a food additive. It's a superfood. So what would happen if we could make electricity from this seaweed? And this is actually what we showed that we could do. In fact, we're so successful that we have now established a startup company called Electroalgae, and you can search for this on the website. And they are now trying to actually commercialize this idea to make enough electricity to make this commercially viable, perhaps in order to lower the price of growing the algae in order to use this in the future. And this is the way we try to do things at the Technion. We have these kind of crazy ideas, start to work on them, start to maybe get some results that show that there's promise, and then maybe even bring them into the marketplace and do something to benefit the world. So I hope that I was able to give you a little bit of ideas about what we're doing in my lab, but enough of me. Let's hear from our young scientists that are with us today, and I'm really happy to introduce my colleague from the Schule Faculty of Chemistry, Assistant Professor Charlotte Vogt.
Thank you so much.
Oh, and I should say,
there was another slide.
There was one more slide, but that's just showing that we really do believe that we can make a better world. There you go.
Thank you. Thank you, Noam. So my name is Charlotte Vogt, indeed. I came to the Technion from the Netherlands about 5 years ago, started my lab at the Technion 3 years ago. And we work in the field of catalysis. Most people know the word catalyst from their car catalytic converter, but they're actually everywhere, as I'll talk about in the next slide. And the basic principle of what a catalyst does is it provides a pathway, like a tunnel, through the mountainous landscape that you would otherwise have, which is involved in chemical reactions. Or as I otherwise like to say, it's like a chemical magic wand. It makes stuff happen which otherwise wouldn't happen. And they're everywhere. They're currently responsible for about 1/3 of the world's global gross domestic product already. A lot of it is in oil conversion. Most of our energy demand is relying on catalysts entirely, and they're also responsible for most of the greenhouse gas emissions, or involved in most of the greenhouse gas emissions. I wouldn't say responsible, because we still need the energy that we're producing with it, right? But the basic concept is that catalysts are used to make something out of anything much faster and using much less electricity. And we started to be able to use them about 100 years ago. And since then, we're actually making them in almost exactly the same way as we were at that time, which is we just try a bunch of stuff together, trial and error, and then we see if it works. Now, it's a little bit of an exaggeration. The last 20 years, we've been able to understand better and better sort of which ingredients are supposed to be put together in order to make a better catalyst for more efficient processes using less energy. But we're still not able to decide, say, I want to make out of a CO2 molecule jet fuel, and I'm going to use exactly this catalyst with exactly this amount of this specific metal and in this specific shape. We're not able to do that yet. And that's the basis of what my lab is built on. And we try to tackle the big problems, obviously, that we're facing, and one in particular. I also have a degree in business administration and MBA. And I really like to think about the huge challenges that we have, for example, CO2 reduction or CO2 sequestration in terms of the economics as well. Because at the end of the day, we have to apply these processes at a huge scale, at the gigaton scale, to be exact, multiple gigatons per year. We have to take carbon out of them. Standing in front of my pretty picture, I'll go to this side. We have to take carbon out of the air in huge, huge, huge amounts, and it's going to be an energy drain. So the idea that we have is we need to make money, in essence, while at the same time sequestering carbon. We have to do something that's economically beneficial to somebody at a really large scale, while also removing and sequestering carbon while doing it. And another really important idea to keep in mind is that we have to understand where we're taking the CO2 from if we want to expend the least amount of energy that we can into it. What I mean by that is, in the atmosphere, we only have a little sliver of all of the carbon that exists in the world, and it's also in the lowest concentration that you can find, 400 ppm, parts per million. In the oceans, we have more than 80%, actually 88% of all carbon which exists on Earth, and it's also 2 orders of magnitude, so 140 times more concentrated than it is in the air. And we know from sort of basic principles of economy and chemical engineering combined that the more concentrated your feedstock is, so biomass would actually be the best example because that's almost solid, complete carbon. The more concentrated your feedstock is to begin with, the less energy you have to put into it in order to make it the product that you want. And so getting it from air is going to cost you 2 orders of magnitude more electricity than if you were to get it from the ocean, where it's 140 times more concentrated. And just to illustrate, we can think of the solutions that we have today, which you might know, which take carbon dioxide out of the air, like direct air capture, or DAC for short. And if we were to calculate their energy consumption, which is the minimal energy consumption that you can ever expend, let's say if you were if you had the best technology in that area, you would still be limited by certain thermodynamic laws. Then in 2038, you would be at the max of the energy that you can spend for that specific process. And that means that we won't be able to ever employ that type of a technology on a large enough scale. And so with all of that in mind, what we do in my laboratory is try to look at catalysts with spectroscopy. So we try to look at the interaction of light with our catalysts in order to understand exactly how to make them much, much, much more active. And by doing this, by understanding exactly which specific sites on the nanoparticles are orders of magnitude more active than other sites, we're able to come up with a process using the ocean's water, which is already allowing us to operate at 2 orders of magnitude higher efficiency with extremely good catalysts, which will allow us, in essence, to expend only less than 1% of the global electricity consumption that we have right now, while also doing something special, which is cleaning the water of the sea from specific pollutants. And so that is the current technology that we're spinning out of my lab. Mosaico is the name. These are the amazing students who were involved in coming up with this technology. And with that, I'd like to pass on the program to my colleague, Charles.
Hey, thanks, Charlotte. So we'll change gears a little bit, but not that much. But it's time to talk about plastic, right? Plastic is another big environmental issue that we need to think about in the Earth Day. And you probably know we live in the plastic area, plastic age, sorry. Everything nowadays is made of plastic. I remember when I was a kid, you go to a place, you want to buy something, and you have it made of plastic or made of metal or made of wood, and you think, oh, don't take the plastic. The plastic is the worst one. It's low quality. If it was the lowest quality material, we wouldn't be using it so much. Nowadays, everything is made of plastic. So for example, the bottle of oil is obviously made of plastic, but the oil inside that, the oil that we use in cars, they are about 20% plastic as well. The paper cups that we use not to use plastic, not only their lids are made of plastic, but the glue that it's keeping it together is made of plastic. You know what happens when you wet paper? This paper doesn't wet. Why is that? Plastic. And as I said, the materials are getting better and better. We have plastics that are stronger than metal, tougher than metal. And that's why nowadays, the latest Boeings, not that we should say good things about the latest Boeings, but they are about 70% plastic. So plastic is taking the roles of all the metals, and it's really becoming more and more the material of choice in the world. And therefore, it's creating problems because plastic is what we are throwing out. And plastic, one of the good things about it is that it maintains its property for a very long time. That's why you can have airplanes that work for a very long time, or you use it in cars, or all the water tubes that we use in houses and in construction. We are changing from metal to plastic. But that's also the issue with plastic, right? It lives for a very long time. So when we throw it out, we accumulate, and that's causing additional problems. For example, if it's open to air, is slowly decomposing and releasing carbon into the air, related to what we were talking about before. But also, as you know, some of this is going to the oceans and causing problems with the biosphere. So most of you have seen these numbers for plastic and these symbols of recycling. So this is actually just a categorization of the plastics we most produce and most throw away. But actually, most of these plastics are not recycled. So PET, the number 1, is the one that we use in our water bottles, and we recycle about 20% of it. HDPE are the ones that we use, for example, for water tubes. And the ones that are in water tubes, we don't really need to recycle because they're going to stay there for hundreds of years. But we also sometimes made the cap of the bottles out of this HDPE, and then we throw them out and we don't recycle it. Polypropylene we use for making chairs and different materials, and recycle a little bit of it. And every other type in here, we actually don't recycle, right? So please don't look at these symbols and think about, oh, we can recycle every one of these plastics, because that's not the case. However, they are very important in the recycling process, because one of the most important things when thinking about recycling is how can we separate one type of plastic from the other? Because the biggest challenge in plastic recycling is actually this mixture between different plastics. If I have two plastics that are mixed together, say polypropylene and polyethylene, or the PET and the HDPE of the cap of the bottle, and we melt it together to make a new bottle, the two plastics just don't mix with each other. So we melt it, we make a new bottle, the bottle looks perfect, but then you press it a little bit, it breaks, it makes a hole. Right? So the biggest challenge in recycling is actually how can we separate between these plastics? And I don't know, in the US, if you take a bottle of Coke or something else, you have the bottle made of PET, you have the cap made of polypropylene, and then you have the polyethylene around it to give it the name and all that. Some countries have actually started to change that and require these plastic companies to make the whole bottle out of the same plastic, because then we address some of the challenges in here. Other problems, there are colors, additives, different additives that come into the plastic that sometimes complicate recycling, but that's less of an issue compared to that one. Different feeds, if you go, for example, to Dow Chemicals and you want to buy polypropylene, you're going to have 20 types of polypropylene. So each company wants to buy the one that it's good for it. But even if you were able to get together only polypropylene, then you're going to have different feeds, and it's not going to be good for any specific process or any specific company. And the latest problem, which is actually a very big one, is price. And this is connected to energy that we were talking about. Plastic is very cheap. That's something good, and that's something bad. It's great because we can make anything out of it and good materials. The bad thing is that any process that we do, for example, related to recycling, is going to be more expensive than buying a virgin material. So I'm a chemist. That means that I'm looking at plastic from a molecular perspective. And just to make things simple, I took here two different plastics, polyethylene and PET, and we can put them as long chains. Those are polymer chains. That's the plastic material. And as I said, if I just take them together and melt and make a new bottle, the bottle is going to be terrible. But the field of study in my lab is called mechanochemistry, which means chemical reactions that happen under mechanical stress. And we have been studying plastics for the last 10 years. And we've always been looking at this idea of taking plastic molecules and breaking them apart into smaller polymers. And one of the interesting things we found is that under specific conditions, we are actually able to break mixtures of these plastics. And about 20% of these mixtures of this PET actually is able to bind into the polyethylene and make new polymer chains in which the two plastics are connected to each other. And the nice thing about that is that, as I was telling you about this recycled bottle, that we have the PET separated from the polyethylene, these polymers on one hand want to go to the polyethylene phase, the other side wants to go to the PET phase. So it ends up that it sits at the interface between the two plastics, and that ends up gluing between them and possibly improving the mechanical properties of it. So to get a proof of concept of something that is more useful, we went to one of the most challenging materials to recycle, and that's what's called the multi-layered materials, which we use in food packaging. So food packaging, we have a layer of PET that we want so that air doesn't come in or go in or go out, so the oxygen doesn't exchange. But PET, as you know from the bottles, it's very brittle, very hardy. So what we do is we put a layer of polyethylene under that, and then on one hand we have a material that it's really soft, on the other hand we have a material that doesn't allow air to go through, and then we have a bunch of other things in the middle because it's really hard to connect between the two. But as I said, this is a plastic that we make, we use it once and we throw it out, and this one cannot be recycled. If this type of plastics gets to the recycling company, they just throw it out. And we said, let's test this in our process. So we just shred it into small pieces of plastic. Then we do our mechanochemical process. So we apply mechanical energy using a device called high energy ball milling. We cause this reaction where molecules break apart and reconnect. And then we take this that come out of waste and use this as a compatibilizer, a glue that is going to help my material with recycled plastic work better. So we put it through a compounder that melts everything together, and we make new plastic bits that can be used to make different materials. So we need to test the mechanical properties of this plastic. So we make these samples that are called dog bones, and then we pull them. And I'm just showing one property here that's called strain at breaks. It means how much can the sample extend before it breaks. So if you take just pure virgin low-density polyethylene, it can grow to about almost 5 times its original size, and then it fails. I didn't show 40% recycled, but there are some commercial additives that can get quite nicely the properties back with 40% recycled, but this is kind of the limit, and the European community is actually raising the requirement for plastic in Europe to have 55% recycled. So we went to 80% recycled material, that it's about 60% polyethylene, and the rest is PET. And we used our compound at only 1% coming from waste as an additive, and even compared to commercial additives, we get properties that are even actually better, a little bit better than original polyethylene. So typically when we recycle plastic, we use it to make chairs or new toys, something that it's no solid plastic, but true recycling means taking what it was made of and remaking it. So we would like to make films out of this the recycled plastic. The issue is that when you make films, you actually make like a balloon. You melt the plastic and you blow hot air in it and you extend it. And naturally, the recycled plastic is terrible because that's extension and that's when it fails. But using our process, was actually the first example when we could get not 80%, but about 20% of recycled plastic into what's called a blow molding process and make new films of plastic. So that's what I had to tell you about plastic. And now I'm happy to invite Professor Adira Dian from Civil and Environmental to tell you a little bit more about our research.
Thank you. So my name is Adi. Thank you for the introduction. And I started my lab at the Civil and Environmental Engineering faculty here at the Technion at 2016, the Soil and Environmental Chemistry Lab. And what we're most interested in is trying to understand what happens to pollutants when they enter the environment. So what is the fate of different types of pollutants, industrial chemicals, pharmaceuticals, agrochemicals, any type of pollutant, what happens to it when it enters the environment, when we have a spill or a leak or anything of that type of interaction. So what happens when it reaches the soil? Does it stick to the soil particles? Does it leach down into our groundwater? What happens when we introduce it to sunlight? Does it break it down, or can bacteria degrade these different pollutants? We're really interested to know what happens to these pollutants when they enter our environment. And we really want to understand whether they enter our drinking water and whether we see them again in our food. So that's one part of what we do. We try to investigate what happens to these pollutants in the environment. And through these investigation and research projects, we try to see if we can develop any new ideas or methods to clean up the environment once we do have a polluted area, polluted soil or polluted water. So what I'm going to show today is 2 different types of research projects, one looking at the fate of pollutants in the environment and the other one looking at ways to remediate polluted environments. So the first project I want to show is something that we've been working on for a while, which is trying to understand the fate of microplastic fibers in soils. So when we buy new clothes that are mixed with synthetic fibers, polyester or nylon, and we wash our clothes, small microscopic fibers enter into the wastewater stream, get to the wastewater treatment plants. They're usually separated into the solid sludge. And in many areas, that solid sludge is taken, composted, and then applied to agricultural fields as compost, as biological compost. So agricultural fields have become a sink for microplastics in general and microplastic fibers specifically. So we've been looking at how these microplastic fibers are acting once they are introduced into the soil. And we start very basic. So we take polyester and nylon fibers and we cut them into exact sizes in the range of sizes that are known to be found in different agricultural fields. So in this project here, we were looking at sizes ranging from 50 microns to about 1 millimeter in size. We dye them so we can track them through our different systems, and we try to understand what happens to them. So what I'm showing here is just a sand column, and we introduce these small fibers and we track them through the column and we try to understand where they stick and how far they actually transport through the column. And sand columns are actually the type of soil where you'd see the most transport. So wherever they travel in sand, that's the most they'll be able to travel. And what we actually found was that any fiber that was larger than 50 microns tend to stay in the top part of the soil, in the first centimeter of the soil. And they stay there, and since they don't get degraded, as Charles said, they have properties that keep them very stable. They start to break down and peel mechanically, and they become a secondary source of pollution. So what we can see here from the images is that they slowly break and peel, and they become the source for small nanoplastics that then can travel, and they can travel down through that column and potentially enter our groundwater or transport to nearby lakes or water. So knowing this, we decided that we want to take an even deeper look into what the mechanism of attachment or of sticking to these particles is. And we created this cell that simulates a porous media like soil. I did this in collaboration with a colleague, Dr. Yaniv Edri from our faculty. And we're looking through a microscope at this microfluidic cell, and we're tracking small fibers, and we're trying to see when do they stick, how do they stick, what is the mechanism. And through this information, we're going to try to predict which fibers are going to stay in the soil and which fibers will travel, and maybe try to think of ideas how to stop them from actually reaching soil. So maybe have some type of filter and know how this filter will work. So this is good for both predicting and for maybe thinking about developing different methods of remediation. The second thing I wanted to show today is the way we think about developing remediation methods. So this is a project that we did to try to tackle the problem of micropollutants in wastewater. So micropollutants are small organic chemicals that are not broken down or removed by conventional methods during the wastewater treatment plant methodology. So these are usually pharmaceuticals, small compounds that maybe are leached out of plastics like bisphenol A, or maybe Teflon-like molecules that are now creating a lot of interest. They can be toxic, they can be problematic. And in places where treated wastewater is used for irrigation, we also know that these small molecules are then added to the soil, are transported to our plants, and they can find their way to our leafy greens. So we were looking at different ways of removing these chemicals, but we don't only want to remove them from the polluted water, we want to destroy them. So we tried to create a platform that is both adsorptive, will remove these molecules from the polluted water, but will also destroy these molecules. And we want to use natural products to create these filters because we don't want to add more pollution into the system. So we look at using natural soil particles for these adsorbent catalysts. And we're working with what we call clay minerals, which are very abundant minerals we can find in soil. For this project, we used a mineral called montmorillonite. Montmorillonite is a fantastic material for adsorption. It's a powder material, a little bit like talcum powder. It has a huge specific surface area. So if I take 1 gram of montmorillonite powder and I spread it out as a monolayer, I get the surface area of 2 basketball courts. So a very fantastic material as an adsorptive platform. And so we took this very natural mineral and we deposited on the surface some iron oxides, also a benign material. And then on this platform of clay and iron, we also added a polymer that the function of this polymer is to specifically target pollutants that we want to remove and adsorb them, or create a platform that is more that has a higher affinity towards these small organic molecules. And the way that this works is that you have a filter with this clay and iron and polymer. And when we pass the water through, the specific molecules that we're targeting absorb onto the surface. And once that filter is spent, we add hydrogen peroxide. That hydrogen peroxide is activated on the iron oxide to create these very reactive oxygen species that break down the pollutants. And they take toxic pollutants, these reactive species can take toxic pollutants and break them down to benign species. So in essence, we have a platform that both absorbs and degrades our toxic pollutants. And we've had very promising results with this platform, and we're now looking at upscaling it. And so this is another direction we're working on. And I just want to end with something that we can all do, not only in our labs, but at home. So small differences that we can make in our daily lives that can make a huge difference in terms of our planet. And I thought of three main things that I think we can take home with us. So one is dispose of hazardous waste properly, so we don't even get those micropollutants in our wastewater. Take care of your pharmaceuticals, of your batteries, of your electronics, of your detergents. Make sure that you take care of them responsibly and throw them away the way that they're supposed to be thrown away. Avoid single-use plastics as best you can. We can each make a small difference in our daily lives and make a huge difference globally. And if you do use single-use plastics, make sure that you throw them away properly. And at the end, purchase responsibly. So only get what you need, recycle what you can, and reuse what you can. And with that, I want to thank you. And we're going to be moving to Q&A, and Mary Ellen is going to help us with that.
Hi, everyone. Thank you so much to our speakers. That was very informative and really, really interesting. We had a lot of questions come in. I'm going to get to those in just a moment. As a reminder, you can still submit your questions. Just hit the Q&A button at the bottom of your screen, and we'll get to as many as we can. So, you know, what I love is that Technion is addressing this important need. And as we heard from Noam, Technion believes they can help in making the world better in this area. We heard from Noam about making electricity from the natural phenomena of photosynthesis through seaweed. We heard from Charlotte about looking at catalysts and making them more active. She's using ocean water to expend less energy to solve the issues of ocean water pollution and removing carbon from the atmosphere. We heard from Charles about plastics from a molecular perspective, a huge issue around the world. And we heard from Adi about different pollutants going into our soil and the important considerations of seepage into our water and food, and finding potential solutions like a filter to help with keeping these pollutants out. Correct me if I got any of that wrong, speakers. But let me jump into some of the questions with that summary in mind. So I want to start. Let's start with Adi, since you were just up. What is the hope for changing the materials used in clothing production, since this seems to be a big cause of soil and water pollution, and can find a way into our bodies as well?
It's a good question. I'm not sure I know the answer to that, because again, designing new types of polymer for clothes is not exactly my area of expertise. Maybe Charles can say something about polymers for clothing. But the idea is always to keep in mind the full life cycle of the products that we create. So understanding that whatever we create and we wear has an extended life cycle after we throw it away. Where do we throw it away to, and how do we take care of it?
Thank you. Yes, I've seen a lot of companies forming around submitting your sort of clothing to them, and they will, dispose of it responsibly. So thank you. Let's go to Charles. Several Israeli companies, UBQ and Alchemy, among others, are recycling dirty or mixed plastics. Have they solved this separation problem that you referenced?
Yes, there are lots of startups looking at that. The material from UBQ, we actually have it in our lab, and it's really fantastic material. Those materials are typically made out of mixtures already. That is not just plastic, actually. they mix wood into that and paper and they have a very nice process. The main issue is how much of it can you actually put back into an use. So for example, some of these materials you can add 5%, you can get 10%, and then it accumulates for the next cycle and the next cycle and the next cycle. So the approach that they are taking is not wrong. It's typically chemically connecting between all the components, which is not different in a way from what we are doing, just a different type of process. Ours is towards mechanical, theirs is more chemical. But the main issue is how compatible it is to where you're putting it back. So for many uses, you can put a lot of these materials and get to decent concentrations, particularly for plastic, just because plastic just hates everything unless it's itself. So particularly for reuse into plastic, that's actually still a big challenge. And again, UBQ, for example, is looking into that. I'm aware of that, but they are not getting to the values, for example, that the community, European community, are targeting for next year. So there is, you have to look at many different ideas and hopefully find a few that work, and then hopefully one or two of them are going to get, to the commercial and industrial reality.
Yeah, no, I'm thinking of, what's and maybe we don't have time for this right now, but what your answer spurred in me is, how does academia and industry sort of work together to find these solutions, right? Like, is it wherever the idea starts, whether it's in the lab or within industry, are you all communicating so that you can sort of, make something greater than what you would individually be doing?
Yeah, so if I can say a word on that, I think that Israel is almost the best place to do collaboration with industry. I mean, we have a lot of our funding, our grants for funding our research. If you collaborate with industry, there are just so many of them. And we don't typically talk in Israel like in the US. They talk, oh, I work with Coca-Cola, or I work. So here we're kind of limited about talking who we are working with. But as I said, my research was on the science side, thinking about how molecules break mechanically, plastic molecules break mechanically. And then suddenly the Israeli plastic industry had this urgency for the European community for next year. So they turned to all the universities in Israel, including me and other groups in the Technion, and said, we have this problem, we need to address it. So all this project that I showed you, I mean, I don't have the ability of making this balloon in my own lab. This is a pilot project that was done with one of the plastic companies. All this project would not have occurred without this communication. And I think Israel is really one of the best places for that.
That's great.
Perhaps I can interject here, Mary-Ellen.
Yeah.
Technion recently realized that we have difficulty sometimes in bringing our basic science ideas into the marketplace and working with industry. And so we established a new vice president for innovation and industry contacts, Professor Lihi Tselnik Manor. So we actually have somebody whose really main focus is helping researchers bring their ideas to industry in a way that will be beneficial for the industry, for the world, of course, because it has to be commercialized to really be efficient, but also to help the researchers proceed with their basic research, because in the end, the new ideas is going to come from basic research, from ideas, from the trial and error types of things that Charlotte spoke about, the ideas that you heard about today. It all starts from really basic science questions, but it goes all the way to industry, and we're really trying to make that much more efficient.
That's great. Charlotte, I have a question for you related to enzymes. Do you include enzymes among the catalysts for capturing dissolved CO2?
Well, so I said that biomass is, we can say, one of the most efficient ways to convert, well, you're converting solid into solid, right? So that's comes at a very low energy expense. I'm coming from a background in the chemical industry, and I mean, enzymes are nature's optimized catalysts. You have, 10 orders of magnitude higher activity sometimes in enzymes than you do in the catalysts that we use in industry. Yet the catalysts that we use in industry, we're still using them. 95% of them are, actually the same type of clay materials that Adi was talking about, with some metal on it. And so they're not enzymes. And the reason for that is that enzymes are relatively easy to kill, or they have to be used in very specific environments. And the same can be said to a certain degree about biomass, or similar, let's say, disadvantages are there. They need a lot of area to grow. And we have used so much fossil fuels, so many fossil fuels. We've emitted so much CO2 that the areas that we would need in order for biomass to convert all of the CO2 back into biomass and then, eventually fossil fuels, it would really start to eat into our food supply. And so we need to have, processes which can be applied at a huge scale. And for that, inorganic materials, so materials like metals, are more easy to manipulate. And because we can manipulate them, then they require, much smaller areas. That's the way that the sort of the chemical industry works nowadays, and it is for a reason, I believe.
So the answer is yes, sometimes?
Long story short, we're studying them because we're interested to learn the tricks. Like I said, they're up to 10 orders of magnitude better than the catalysts that we currently employ. So we do study them, but from a very fundamental perspective, in order to understand how to make our own catalysts much better.
Got it. Understood. Thank you for that clarification. No, moving to you. Is there an advantage to making energy from algae, for seaweed, as opposed to other sources of clean energy?
Well, certainly the first advantage is if you're growing it anyways, or it's growing by itself. For instance, the seaweeds which grow, they can grow 30% in biomass per day, just by in the seawater. And if you're using them as for something else anyways, so there's a big benefit, because today almost all energy that you create is the only thing that you create. So if you make a solar cell, there's a lot of pollution going into making the solar cell. You have to bring the solar cell from wherever it's manufactured. Much of that is in China, for instance. That's why the prices have gone down. So you have to transport them by ship. You have to install them. And that's all they know how to do. They only know how to make energy. But if you use a plant or a seaweed, then you can do something with it. Like perhaps if you go back to the olden days when people used the same let's say, animal for many things. They used the meat for food. They used the skin to make a tent. They took the bones to make something else. So here you can use it for food or for pharmaceutical or for a cosmetic, and you can also make energy at the same time. Does it have downsides? Of course it does. It's not as industrially easy to extract large amounts of energy from the seaweeds so far. That's what the company is trying to do. But certainly it has certain benefits. I think that something that Charlotte said is absolutely correct. Enzymes have great capabilities, but they are generally much more sensitive to their environment than inorganic catalysts. So many industries continue to use these superior catalysts. Others use enzymes, but know that they only have a short lifetime. Same thing is going to be in our case. Probably there's going to be a short lifetime. But again, if you use it for another thing, that already makes it probably better. Now, if you can make hydrogen, then that's even better, because hydrogen now you can transport and use it in your car or in your home. My dream is to mow the lawn in the morning with a mechanical mower, not an engine. So I'll also do a little bit of sport. Put the clippings in a machine, go to work, come back, and have enough energy to run the house.
So we had a question related to portable fuels. Is hydrogen one of those portable fuels?
Hydrogen certainly is. Today, we already have hydrogen operated cars. In fact, right down the road from the Technion is the first gas station that has a hydrogen producing a machine. So we have a few trucks now that are run by hydrogen. The pollution from hydrogen is negligible. It's really basically water that goes back into the atmosphere. There are issues with hydrogen. It's not simple, but these are being overcome. By the way, there are other companies in the Technion that are interested in making hydrogen in a clean fashion. And if you go to that website that I already mentioned, you might see links to these different companies that were established by Technion faculty members to make clean hydrogen.
Fascinating. Okay, back to plastics. There's a lot of questions around plastics, and I think it's because it's so part of our world, right? Can plastics that you cannot recycle be burned to create energy safely?
Yes, so nowadays about 20% of the plastic waste is actually burned to make electricity or heat. And there are issues with that, right? So there are issues of pollution, there is issues of connecting between the plastic issue, the plastic environmental issue with climate change, because when you burn, you get CO2. But some of the, and nowadays we don't choose what we burn, right? The plastic waste that is around, that's the one that we burn. One of the biggest issues right now in Europe is the wind blades from wind energy, that they have a lifetime of between 20 and 50 years. And they're made of a very, very strong plastic, the same ones we use to make airplanes. And those ones we are taking down and we cannot recycle and we cannot burn them. Or it's very, very hard to burn them. You end up consuming more energy than you get. So not every plastic can be burned. The ones that we produce in larger amounts, they can be burned, but you have to consider the negative effects it has in other environmental problems, right? In a way, plastic is, I don't want to say that it's the opposite of of climate change, because it's about, as Charlotte said, carbon in the air and carbon down here, right? So plastic is carbon in the solid state that it's going to live for hundreds of years and doesn't get to the air unless you burn it, right? If you burn it, you end up solving one problem to create another problem.
That's right. Yeah. Okay, and this might be either Charles or Adi. So won't the merging of shorter strained plastics into new materials make it harder to recycle plastics at a next generation level? Isn't breaking plastics down into separate materials better?
I guess this is better for me. So as I said, if you go to Dow Chemicals and you look at polyethylene or polypropylene, you're going to have 20 types. And one of the types is the one, you don't break them forever. You break that there is a minimum size and you can't break it beyond that. And this size is actually perfect for one type of process, which is, for example, which is called injection molding, which is really doing like plastic things, like doing plastic chairs or toys or pipes, right? Everything that is solid plastic, because of the process of melting and injecting it, you would like it to be the shortest chain that you can get. So actually, our process, it doesn't help every single plastic industry. We cannot re-inject after our process for any plastic company, but we can definitely reuse it up to 80% for things that are, solid plastic. And as I showed, with a smaller amount to materials that are making new films. So for those types of processes, the shorter chains are actually better. And I didn't get into that, but again, looking at those challenges, I said that there is separation and there is the different sources. By breaking them all to the same time, the same size, we're actually homogenizing the type of polypropylene or the type of polyethylene. Now it's like I got it from Dow. Everything is the same size, and it has these properties, which are not great for everyone, but it's certainly great for this specific type of, these specific industries.
Yeah. Adi, this question I think is for you. So the technologies that are happening between you and Charles and your labs, how can these technologies be used to clean brown fields?
Brown fields?
Is that, I was hoping that you would know what that meant. It's not, the term is not known to me.
I'm not
Okay.
sure what a brownfield is. Yeah,
Okay.
I'm not.
All good. We will move on to a question for Charlotte. And it's a broader question. An idea, Charlotte, on what brownfields are?
Yeah, exactly.
So, this is all amazing technology research that's happening at the Technion. Right now, it's happening in your labs, and potentially in industries around Israel and elsewhere, we know. How much time and dollars will be needed to reach a scale to solve even 5% of the Earth's pollutants? And I'm starting with you, Charlotte, but obviously this is a question for all.
Of the Earth's pollutants.
Wow.
I mean, as we go, we're going to evolve into what pollutants will exist. So let me just grab what's closest to me. And I guess also one of the biggest, if not the literally biggest volume of challenge, which is CO2. I believe that, I mean, if you look at the sort of historical prospects of new technologies, what I was trying to show in the slides, but I didn't explicitly say, is that typically you can see that new technologies, and it doesn't matter if it's a sustainable electricity or a sustainable technology, or if it's fossil fuel based or nuclear or what have you, typically you see that you have exponential growth in the deployment of these technologies up until it hits about 1% of the global supply and demand of electricity, and then it starts to grow much more slowly. And this, I mean, this is logical. You can't make all of a sudden next year, 10 times more stainless steel, or things grow slowly. There's amortization that you have to take into place, that you have to take into account, and these billions of dollars invested in fossil fuel electricity production facility. You can't just tomorrow decide to go to something else, right? And so we have to take all of that into account if we choose or let's say to decide which trajectory we're going to take. And I think that right now, a lot of the decisions that are being made by legislature, they're going towards a direction where let's say lots of dollars are invested in technologies which have the potential to become obsolete. So what I love about Israel, and what I love about specifically also the Technion, is that there's a very close interrelationship between scientific innovation and actual deployment. And so I think that the technologies which are going to be groundbreaking, which have the potential to break even something like this, the normal deployment rate of energy type technologies, are going to come from a place like this, from my colleagues, which I think is a really cool environment to work in. I know that was a really long answer and a very vague answer into the specific question, but I think that we need to change the way that we're thinking about these types of technologies and employ things which are which can grow exponentially as fast as possible. And that means many different things. That means potentially using 30% gaining in biomass in a day. I had no idea. That means deploying a carbon capture technology which can forever grow exponentially because it's using so little energy, right? So it's never going to be one specific answer, and it's very difficult. It's futile to give an amount or a certain number of years. But I am extremely optimistic. I think that humans have overcome not much larger, have overcome very large challenges in the past. Global famine 100 years ago, which is why catalysis was really industrialized in the first place, making fuels out of all kinds of crazy things and under difficult circumstances. So I'm positive that we'll be able to solve this, but we need many different people working in many different fields to find all of the different types of solutions which are necessary. And that was an even longer answer. I'm sorry.
If I can add on to the long answer. So what Adi ended with is really important, because the way all of us behave in their day-to-day life is going to reduce the amount of pollution faster than the scientific solutions that we can provide. But science is needed to really solve the problems that we're going to have in any case, because in our modern day life, we have needs and we have requirements, and we're going to continue to use materials. Just to give an example, today we have more and more electric cars with larger and larger lithium-based batteries. And we're going to have a lot of pollution in 10, 20 years with these batteries. And people are already working on overcoming the problems. This was a good solution, and there's less pollution because there's less use of gasoline, but it's a problem that we're going to have to overcome. So the more responsible that we are on the personal level, on the governmental level, is going to improve how us as scientists can give better solutions to solving the problems that we can't solve otherwise. And of course, when asked paper or plastic, ask for paper.
Always, absolutely, paper. Thank you. Thank you all so much for this wonderful conversation. I mean, there are many more questions. I have more questions. I wish that we had more time. We will, audience, we will get answers to your questions and send those along with the recording. If you're interested in learning more about anything that you heard today, and the amazing research that is happening at the Technion by these four, by other faculty members of the Technion, please reach out to your local ETS representative or send an email to info@ets.org. This program has been recorded and you'll receive a link, and we'll try to include all of the answers to the questions. I want to share our sincere thanks to Noam and Charlotte and Charles and Adi. And for joining us today to share just some of Technion's incredible work towards slowing climate change around the world. I can truly say that I feel better knowing that great minds such as yours are working tirelessly to solve some of these difficult issues. A reminder of what Adi said at the end: dispose of your hazardous waste safely, avoid using single-use plastics, and purchase responsibly. Thank you all very, very much. Wishing you a happy Earth Day and a warm and wonderful Passover. Bye, everyone.
Bye.